Okay. Hmm. Okay. Let's see how this is going. Okay. So I don't know if I. Hi. So I firstly need to go through some notes that I studied earlier, and yeah, this is actually it. I'll be going through some basic revisions, and then I'll start studying some fresh material. Okay, so the name of the course that I'm now is Statistical Learning, and is one of the most fundamental uh, says, or areas in machine learning and data science. Um, and basically, the rules of this study session are simple: study as much as I can. And let's see how long this study session will be. Okay, so um, statistical learning refers to a set of tools for understanding data. Statistical learning theory is a framework for machine learning derived from the fields of statistics and finance and functional analysis. Statistical learning is a set of tools for understanding data. Statistical learning theory is a framework for machine learning derived from the fields of statistics and functional analysis. Statistics can be classified as supervised or unsupervised. Broadly, supervised statistical learning involves building a broadly speaking, statistical learning involves building a model for predicting outcome to an output based on form and input. In uh, in supervised learning, the inputs but not supervised outputs. So basically, what is statistical learning? Statistical learning refers to the vast set of tools that I use or can be used to understand data that are used for understanding data to understanding data. So basically, when we're talking about statistical learning, we're talking about anything or everything that has to do with the tools that we can use to uh, understand data. So, for instance, when we have a problem in data science or machine learning or AI, the main entity or the main ingredient, I would say ingredient, but the main requirement is the data, of course, because without the data, there's nothing that we can do. And that's what statistical learning does. A lot of tools that can be used to interpret and understand the data. The two branches of statistical learning, um, supervised and unsupervised learning. When we're talking about unsupervised learning, this is when we have uh, certain. The, when when we're talking about supervised learning, it's basically when we have labeled data, and labeled data just means that a mapped we have a mapped data set, so to say. We know the inputs, and we expect the output from the inputs that we have. But when we're talking about unsupervised learning, we have no labeled data. We just input the data, and we just want the model that we use on the data to work magic. So that is what statistical is in simpler terms. Okay, let me just write a quick note. Now, oh, right. So, um, so this is it. Let me try to see if I can remember. Let me try to see if I can remember. Like, what I'll try to do is for every subheading that I already studied, I'll try to explain it before I read the note. So, like, this is just basic notation. The notation that is used is N for number of distinct data points or observations. P, number of variables available for use in making predictions. I, index samples of the observations from 1 to n. J, index the variance from 1 to 2. Rows of x1, x2, rows of columns of x. So rows are denoted by n, and columns are denoted by p. Yi denotes the ith observation of every one of your vectors of line, and will be denoted in what case board. Mhm. Remember this upper scalar object. A is Mhm. um, um, input variables are usually denoted using the symbol x with a subscript to distinguish the input variable by different names. Predictors, independent variables, features, or just variable terms. The output variable is often denoted using y. The output variable is often called the response or dependent variable. Mhm. So this is a very minor, crucial statement to understand. So there's a statement here which says input variables are sometimes called independent variables, and the output variables are sometimes called the dependent response. And this relationship, the output and the outcome, is what they're called independent and dependent. So this basically entails is that if x is called wait, I don't know if I can divide this. So basically what this entails is that if x is the independent variable, it means that it has a lot to do with how the outcome y will come out. So basically, therefore calling y the dependent variable. You know, x is independent because it's a feature, it's a predict. It is the s- sample in the data that we actually have information about when we're talking about supervised learning. But in most situations, y is just something we can predict without looking at the data. But basically, all the information that we know about x, oh, sorry, all the information that we know about y is derived from x. And there's an equation that's very interesting. Let me write it. I don't know if I remember it, but it's from school. So there's this equation yx is equals to mx plus b. It's very interesting, and shortly after, I'll just, I don't know, show you guys a little bit of why it's interesting. Mhm. Okay, okay. Um, Suppose that more generally we observe a quantitative response y and b different, whereas not that there is no x, which can be written in the form. Huh. So just as I showed this y is equals to mx plus b, in statistical learning, there's also a similar, I can't say equivalent equation, but it's basically almost the same. The variables are related in the same way. And it is this. So this second equation uh, maps the relationship between y and x, or the relationship of y to x. What this basically means is simple. So just as I say, um, I'll try to explain, because right now I'm trying to revise. So I'll try to look at the notes. I'll try to explain the concepts before I read the notes, because I want to see how much I remember from this. It's been weeks since I started. So this equation here, as we talked or discussed, I don't know if this is a lecture or a discussion, but it's just me studying. But that's how I actually normally study. Like I don't know, I always talk as if I'm in a lecture, like I'm teaching or something like that. So basically, this equation, let me see if I can find it in that actually. Let me see if I can find this equation and then is this fast? Mhm. So, um, this is one of the best interesting books I've ever read in my entire, you know, 3 years or so in university, and it's because of how well it helps you understand a concept, building off from very simple concepts, very simple equations that you know we've learned since high school, and then it just builds up from there. That's one of the best books that I've read so far on uh, I'm trying to look for the equation. Where is it? I don't want to skip it. Like, okay. Uh-huh. This equation. How do I zoom in? How do I zoom in? Mm, how do I zoom in? Ah, here. Huh. So this equation maps the relationship between y maps y to x, and basically the best way to understand this equation is like this. We have four variables here. We have y, f, x, and this last term, which is called the error term, and it's there. There are, I think, two different types of errors, and this is called the irreducible error, and We'll talk about that in a second. But basically, this equation it tells us says one thing: y is equals to f of x plus the error term. And in statistical learning, this is how we understand the equation. So as we looked at, like as I mentioned earlier, y is the output, which is the dependent variable. And this variable is dependent on x, which is the independent variable. And so the beauty about this is if you understand them from the basic definitions, like this is the dependent and this is the independent variable, you standpoint can look at how it translates into an equation. So here, since we know that y is dependent on x, therefore we can, with some certain confidence, conclude that if we know something about x, it can tell us something about y, because y is the solution that we want to come up with, the solution that we want to find in the situation. So f of x now. So this is the relationship. This is why y is equals to this stuff because um mm, because when you put everything together, you know something about y. I don't know if that makes sense. So what is f? F is the information we know about x. F is the information that we know about x. This is very simple. So f of x is a function, right? So let me give an example. Let me try to think of an example that would make sense in terms of how uh, f is the information about x. So mm, let's say you have segments, right? You have segment A and segment B, and x is our input variable. So we know that x belongs to segment A. So we know that, so this is a perfect example here. Let's say we have two segments, right? Segment A and segment B. Now, from what we know about x, we know that x belongs to either of these segments, segment 1 and segment 2. So, what exactly is f in this situation? F is the information about that we know about x, right? So, in this situation, f would be uh, a range that tells us that tells us something about x. Maybe it would uh, f is, two or whatever. This is really funny. Like, I know how to explain this example, but I'm just getting lost in thought at the same time. Okay, let me try this again. So let's say we have two segments, segment A and B. If f is the variable that is the information, if f represents the information that we know about x, and we know that x belongs to either of these segments, for us to determine which segment exactly x belongs to, we can use the information that f provides, and this information can be if, and it could be information like f has got these properties. It has a range of 0 to 2, 0 to 1 set. And if we can find that range in either of the segments, it means that that is where x belongs to. So f is just basically the systematic information that we know about x. You know, it's like uh, it's like it's like you're playing a game, right? You're playing a game, and the clues that you get along the way to your objective is f, so to say. That's f. Do you ever play a game and you don't know, you're standing in a location and you don't know what to do? You don't know which direction to go, and there are hints. That's what basically f is. And now let's look at the last term, e. E is the error term, and in this case, this is called the irreducible error. And what that means exactly is very simple. So, statistical learning or machine learning has got a number of objectives, but at the core of everything is trying to make sense of the data that we have before us, right? But when you create a model from a certain data set, it understands how to solve certain tasks. But one thing, if I was an AI model right now, I would be hallucinating. This is what it fools you. So basically, in simple terms, let me not try to mm, let me not try to complicate things. Basically, uh, basically the error term is, it's called there's the reducible error and the irreducible error, and this is the irreducible error because of one reason. It is the error that no matter how well we fine tune our model, no matter how well we try to make it perfect, this error will always be there because if I remember well, it has a mean or standard mean of like zero or something like that. But in simple terms, think of it this way. This is actually an example from the same book. Uh, if we Let me see if I can very well. It's been a long time since I read that. So if we want to determine if we want to determine uh so let's say a patient comes in with let's say a patient comes in and this person is uh what am I trying to say? Okay. So I remember the example, but it's going to come in handy later on. But right now, I don't even think it applies to this. But basically, the error term is every. You know how we said y sub I this here. Y sub I is like a distinct data point in the sample, right? Like a data point in the sample. You know how each sample basically has unique characteristics to it. Each data point is unique, and this uniqueness is basically something that differentiates all the like. There's always something about this data point that's unique, which makes it uh, impossible for us to create a model that's completely uh, error free because every data point is unique. So for every uh, okay. You know what? This is a revision. This is a revision. I'm not supposed to beat myself down for sucking at this for being so bad. But anyways, yeah. So, um, hmm, okay. So, okay. Now let's try to read the notes. As I said, I'll try to explain what I remember and then read the notes. If so, we have the following equation, and we assume that there is some relationship between y and x which can be written in the general form of that equation on the screen. F is some fixed but unknown function of x. E is a random error term which is independent of x and has mean 0. In this formulation, F represents the systematic information that x provides about y. This is interesting. I think everything that I remembered was not correct. In this formulation, F represents the systematic information that X provides about Y. So I think I explained it in a way that X is the systematic information that we know about X, but rather it's F represents the systematic information that X provides about Y. Wow, that's very interesting. That's very interesting. So basically, in this equation, y is equals to f of x plus errata. This represents. Let me try to do something. Hmm. Hmm. Okay. Okay. Yeah. So okay. So that is a very crucial and critical point to understand. F represents the systematic information that X provides about Y, which is why X is the independent variable and Y is the dependent variable. And for it to be dependent on F, on X, F has got information about Y, and this information is F plus the error term. So the dimensions of the function F depends on the number of predictors. F is is a one-dimensional surface. Two, so F is a one-dimensional surface if we have one input. F is a two-dimensional surface if we have two inputs as well. Okay. In essence, statistical learning refers to a set of approaches for estimating F. Ooh. So, in essence, statistical learning refers to a set of approaches for estimating F. Hmm. This is, I think, very interesting. In essence, statistical learning refers to a set of approaches for estimating F. So basically, the whole field of statistical learning, which is what we're doing right now, is a set of approaches for estimating F. So now the next question is, uh, let me answer. So the next question is, uh, why would we want to estimate F? The two main reasons why we may wish to estimate F: prediction and inference. Prediction and inference. Okay, let me try to see if I remember what inference and prediction is. Prediction and inference. So a prediction is, in this case, an educated guess. So basically, everything that we do in statistical learning is backed by data. So we're not concerned it being, it would take, wait. So the reason why we estimate F is because of two reasons. Prediction first. Prediction is this concept where we are more concerned or we're more interested in the result rather than how we get the result. Yeah, I think this is what it is. So prediction is basically this concept in statistical learning where you're you're more concerned with uh, the output rather than the input. And this is very important later down the line because there's a lot of concepts like how you choose a model and how each model is good depending on what you want. And inference and predictions are like one of the core foundations of understanding what group of models you might consider. So prediction basically involves you just wanting to have a data set, the model working like a black box, which is you don't know how it works, but if it gets desired result, then that's all you want. And inference is basically the opposite of that. You're more interested in how the the more there comes up solutions, you're more interested in how, you know, the model understands data and leading to a certain output. This is what I think those two concepts are. So it says for prediction, in many situations, a set of input X are readily available. The output Y cannot be easily obtained. In this situation, since the error term averages to zero, we can predict Y using. This was interesting. Hmm. In many situations, a set of inputs are readily available, but the output Y can be easily obtained. In this situation, since the error term averages to zero, we can predict Y using. Do you ever just, do you ever just, do you ever just try to study and not remember anything from your notes, as if you're not the one, like you're the one? So we can setting, since the error term averages to zero, we can predict Y using Y equals to F. Let me see if I understand this. Like, where F represents our estimate F and Y represents the resulting prediction for Y. In this setting, F is often treated as a black box in the sense that one is not typically concerned with the exact form of F of X, uh, with the exact form of F hat, provided that it yields accurate predictions for Y. Hmm, this is interesting. So we can use this equation Y hat is equals to F hat of X um, to represent the result in terms of where. So F hat represents our estimate for F, and Y hat represents the result prediction for Y. Okay, so this is interesting. This is actually interesting. This is actually very interesting. So, according to the way I understand this, so so we can use this and we can use this we can use this equation to predict. So understanding this equation is so easy. Well, but trying to make sense of it in like a practical term, it's just something that I don't know why I'm struggling to do a lot right now. But basically, this equation does is the example that I gave of a game, and F is the information that you know helps you get to your target. So this equation is the equation being in a game and trying out certain things in your area, like in your area where you're at, to try and see if you're going to you know find the next clue, the thing that you're looking. For instance, in God of War, or the entire series, basically, there's a lot of puzzles that you need to solve. Like, you go to an area, before you do anything, there's this thing that really annoyed me. You have to kill like a lizard, alive a lizard, and this is what basically this represent. This It's like you're in an area, you know something is supposed to be right, and you exploring it and trying, to pull certain things, trying to analyze certain things, is the equivalent of you using it. You know something is going to happen, but you don't know what exactly. So this is how I understand it in simpler terms. But in practical terms, I don't know. Wait. Yeah, so it says, in this certain, since the error term maps to zero, we can predict y using y hat equals to f of x. And uh, y of x. Hmm. This is very confusing. Where f represents our estimate for f. And okay, I think I understand it now. So we have the equation y f of x plus e. But then we leave out the e because it ever registers zero, right? And the reason why, so we know that f uh, tells us the systematic information that x provides about y. So basically, I'm guessing that when you're in model, you have data and you just have. I think this is what might lead to the concept of fine tuning, which is basically you trying to find the right parameters of, like your features that produce the best results. So basically, we know certain information about. I think it's like, from the way I would guess, we know that the relationship of x to y is within the segment of 1 to 10, 1 to 10, and the best value that cor- the best value that showcases the relationship of x to within this range. And so us estimating which is f hat, using estimates to see which results provide the best response is basically, okay. I think I understand it. I think I understand it. It's into words, which some might argue that, if you can't explain it, then you don't understand it. But I think for now this will. So in this sense, f of x is often treated as a black box, in the sense that one is not typically concerned with the exact form of f hat, provided that it yields accurate predictions for y. As an example, suppose that x1 uh, x1 until xp are characteristics of a patient's blood sample that can be easily measured in a lab. Mhm. As an example, suppose that x1 xp characteristics of a patient's blood sample that can be easily measured in a lab, and y is a variable encoding the patient's risk or severe reaction to a particular. It is natural to seek to predict why he uses, since we can then avoid giving the drug in question to patients who are at high risk of an adverse reaction. That is, patients with the case of why. Was it 20 for whether it was in general, if be a perfect estimate for f at least in error to introduce some error. This error is reducible because we potentially improve the accuracy of x by using demonstrable statistical techniques to. However, if when if we found out the conclusions of them, so that our estimated response took the form of prediction. That is a function of also effect of Theory disease, right? Which may diminish everyone. Potential pleasure. Yeah, okay. There's a way we can talk about it. We can introduce. What is there? Quantity. Quantity. Okay. May content. Hmm. Wow. My skin just get that. Hmm. I think one of the reasons why I would like to move to an apartment is, the ability to just. I like to talk. I like to study as if I'm holding a seminar, or I'm holding a lecture. It just helps me, you know. That's I think one of the most effective ways of studying for me. Is I think it's easier to understand concepts. It's easier to understand concepts, and it helps you in the long run, even when you you haven't studied the material in such a long time. It's easy for you to remember it because you understood the building blocks from it. Some of the most memorable things that happened to me in high school. I was I had a sleepover. We were planning to study and prepare for presentations, right? But it was the first time of us like doing that, so we literally spent, wasting time talking, and we barely studied. And then I don't know. I guess we went. War with books, but we spent more time talking and chatting than actually reading the material. But I was, you know, through the material, and I don't know how. Like, I was looking at the material. I wasn't even actively studying or taking down notes, but I was, we're talking. I'm looking at it word by word, and then the following day, I had to make a presentation on it. And with my high school, you have to like bring your, like a flash drive or whatever. You just had to. Uh, I don't know. You just had you could make flow charts, but basically we didn't do that. And my friend couldn't do the presentation, and then like he couldn't do the presentation, and then for me, I was like, yeah, I'll just do it. I did it, and like a presentation, of which I didn't see any reason why I wasn't going to do it. Not because I didn't study, because for me, I looked at the notes and I remembered what I looked at, you know. And that's how I always did my presentations. It was never really like something like, I need to do this, but just I guess it's an active imagination that has always helped me. And when I did the presentation, my friend was like, "Yo, like we literally did study. How did you remember all that?" Like, he was so he was so perplexed. He started asking like study advice. I was like, "Yo, how did you do it? Like, worry, we're wasting time. We didn't study at all." And him, who actually woke up before me in hopes of maybe he could cover some things, he couldn't really study enough to feel confident that he could present. But I went there, and I think it was a good 20 minutes or so. Just doing the presentation, and I was just talking. I was like. So this is what we had concept, blah blah blah, stalking, I was what, and then the teacher was like, this is how you do your presentation. When you're given a topic, study in depth, you understand the way he's explaining. And I was like, oh boy, And I think those comments, I think those were more public. I think that's why he asked like, how did we, like you barely studied, you didn't prepare for this, I spent the night with you, like where I was, and somehow you did the presentation as if you studied everything. And honestly, it's one of those things like, for instance, you ask them, how did you make it on YouTube? And then like, just work hard, just work hard, just work hard, And that was like, I didn't know what to say because it's like, I don't know how I learned that. I just do it. I did it so flawlessly. Anyway, I don't even know why I was saying that, but yeah. So let's try to get back to the notes. Goal is to basically become a data scientist, and I want to work one of the big, FANG companies or something like that. So I think this equation is just very simple to understand. If we're not talking about prediction, f hat of x, y hat is equals to, I see. Think of this original equation that we had at first as the, I think it's easy to think of it this way. We have y is equals to f of x plus this. From this equation, we can tell that the information that x provides about y gives us this equation, right? So if we, I don't know why I understand this, but I don't know why I'm having a hard time explaining it. Let's see. So basically, when you look at this equation, the equation that was on top, the equation is on top. Jesus Christ. So, what is this? Anyone who gives this research. Mhm. So, I see. I see. I think I can now explain it. So, uh, this original equation that we had, y is equals to f of x plus the error, is the equation that shows us the relationship of the independent variable and like the independent variable and the dependent variable. So, that's just the equation that shows us the relationship, right? Have a data set and we actually want to use this equation, we do not, we don't typically, I would say, we don't get the exact information which tells us about y, and y is basically the output. So we have the information, so we have an idea of the information, but we don't know what exactly it is. So this is us using uh, this is us using this function here, which is the same equation without the error term because it's averaging to zero, therefore it's pointless. Hmm. And it's like we have a range in this situation. We have x plus some certain information gives us y. This is how, but this information, we only have an idea about what it actually is, but not what it is exactly. But we know that if we have certain information, we know the information, we have an idea, and based on the output of, we can easily tell if we're using the right information. Therefore, it's like, as I said, if we have a range of 1 to 10, we know that this information is in this range. So we can try 4, 5, and we'll see the outcome we'll get and compare it to the. I see, I see. So I think this is a tiny picture of the bigger picture, which is, you have split your data into three sets: the training data, the test data, and the validation set. The training data is the data that the model that contains the output and the input and the output, so to say. So the model learns on this data of this certain input, you get this output, right? And when it looks at that, I guess it tries to replicate. I don't know what I'm saying. I don't know what I'm saying. I don't know what I'm saying. I don't you know what I'm saying. Okay. Mhm. But yeah, I think I basically understand this. So this is a statement that's very important. However, error in general, F hat will not be a perfect estimate for F, and this inaccuracy will introduce some error. This is a very important point that I think talked about at the beginning of the session, where it's like, how can I say it? Anyway, it's just an important point. Okay, so yeah, so I think a lot of the time, so I'm someone who's starting. I try to get a good grasp of the basics, which I feel like is something that leads to a lot of people getting stuck in, you know, like the beginner level for a long time because they're just trying to learn and learn everything. But I also fall, victim to so to this as well. But at the same time, I think I just do it just to the point where when I encounter the hard topics that build off of the basics, it's easy for me to understand them because I did, try to cruise through the concepts, so to say. And this is it. When you're talking about machine learning, whatever, a lot of people think about coding, writing, all that stuff. That's good, but it actually comes down to the tiny basics. Training the model is only less than half the work. The entire work is just how well, you understand theory, according to my understanding, I guess. So I just wrote on my thoughts. Mm. So, however, even if we were able to estimate f such that y hat is equals to f of x, our prediction would still have some error in it. Whereas the seventh one, which by the variability associated with the surface accuracy of our model. This is known as random estimate f. We can introduce the error introduced by why is there reason okay. The quantity E may also contain a measurable variation. Consider a given estimate. Why is there so the quantity E may contain a measurable variables that I use when predicting. Since we do not, something that I forgot to do is to go through the case. Okay, I'll do that later. The quantity may also contain unmeasurable variation. For example, the risk of an adverse reaction may vary for a given patient on a day, depending on manufacturing variation in the drug itself, or the patient's general feeling of hoping that. Okay, consider given is the benefit of predictive work, which yield the prediction. Therefore, are fixed so that they are repeatable. And then it is easy to show that consider given estimate f anything of predict x, which you would choose the prediction. Okay, let me see if I can try to explain this. Consider a given estimate of f and a set of predictors x, which shows the prediction y is equals to f of x. I think for a moment that both so that it is easy to show that. Imagine if a girl cheated on you and you are trying to understand why she cheated. everything is about why one is supposed to cheat, what would lead someone to cheat. This is literally the whole existence of this book, which is F. Like what F has to do with, the information it provides in relation to X so that we can know about why. I think it's crazy. So the focus of this book is on the techniques for estimating error with the aim of minimizing reducible error. It is important to keep in mind that the error will always provide an upper bound on the accuracy of our prediction for y. Bound is almost always not. You know what? The best way to actually understand stuff right now, if you want to study effectively, like you don't want to waste time. I found that so right now I'm looking at uh so this labeled part, it is important to keep in mind that the irreducible error will always provide an upper bound on the accuracy of our prediction for y. I don't like really understand it, and I'm trying to like ask AI what it thinks, and it's brought into like this new word that I like. I think it's error decomposition machine learning, which is interesting. So it says when we create a model predict the target variable y from input variable x, the total prediction error gets split into three components: bias error, variance error, and irreducible error. The error caused by approximating a complex reward problem in a model. The error due to sensitivity to small fluctuations of the training data. However, this is a noise inherent in the data. It represents a variability in y can be explained by x. Model houses get a perfect. This is the this is the this is the one which provides the reliability okay, that can okay. It's actually an interesting point. So this is This is, I think, an interesting mm, summary of what the irreducible data is, and I didn't really think of it in this way. So, both x and y are functions of the irreducible error, right? The reducible error. So, the easiest way to think of the irreducible error, which this statement says it is important to keep in mind that the irreducible error will always provide an upper bound on the accuracy of our model for y. And the reason being is since we use x to predict y, the reducible noise, the reducible error is the noise that is within y that cannot be predicted by x. So basically, no matter how no matter how well our model is sophisticated, we just can't use we, we just can't. Someone is fucking talking on the phone. Not a reserve. Pretty good. This statement refers to economic because of modern testing data model predicted this is nice inherent to the data here as a variability in model based on by x. So this point about the irreducible error is very interesting, which says the irreducible error is the noise inherent in the data. It represents the variability in y that cannot be explained by x, no matter how sophisticated or perfect the model is. And the reason for that is pretty simple. Take, for instance, if you want to measure, like, know someone's, if you want to predict someone's height or someone's weight off of their height, you could do a great job of, you know, uh, you could do a job, you could do a decent job of saying if the person is, 6 foot tall, they, might weigh, I guess, 160 pounds. Or we know that for a fact it is more likely, that a tall person is thin. So we can, easily like make these predictions. But we just can't, no matter how hard we try, get the exact uh, weight of this person just going off of their, their height because of a number of reasons. Their bone density, their, lifestyle, their, yeah, all those little factors are basically the 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 the, the little inherent noise in the data that no matter how well we try to predict, this person's weight, but because we just haven't, you know, uh, there are just some things that we cannot explain using our inputs, and therefore, yeah, that that again. So, uh, mhm. ah, so this is this bound is always known in practice. This is because, yeah, I mean, understanding it from this perspective that we can. It's always unknown, not known. I need glasses, y'all. We're often interested in understanding the association between y and x1. to expect. This is your wish list. Now, if not appreciating but people we need to know is that one may be interested in answer during the following which predictors associated with the response. Is it often the case that only a small fraction of the variable item is identifying the few important predictors among a set number in explanations depending on the application? What is the relation between the response of each predictor? Some predictors may have a positive relationship with y, since the data that larger values of the predictor are associated with other values of y. Other predictors may have the opposite relation. Depending on the complexity, the relationship between the response and a given predictor may also depend on the values of the other predictors. Can the relationship between y and each predictor be adequately summarized using a linear equation, or is the relationship more complicated? Can the relationship between y and each predictor be adequately summarized, or is the relationship more complicated? Historically used methods for estimating f have taken the linear form. In some situations, such an assumption is reasonable or even desirable, but often the true relationship is more complicated, in which case a linear model may provide an. Can the relationship between y and each predictor be adequately summarized in a linear fashion, or is it? In this book, we'll see a number of examples that point to the prediction set and the inverse setting or combination of factors. Consider a company that is interested in conducting a marketing campaign. The goal is to identify individuals who are likely to respond positively to a mailing based on observation of demographic variables measured on each individual. In this case, the demographic variables serve as predictors and response to the marketing campaign, either positive or negative, serves as the outcome. The company is not interested in obtaining a deep understanding of the relationship between each individual predictor and the response. Instead, the company simply wants to predict the response using the predictors. The company wants to accurately predict the response using the predictors. This is an example of prediction. In contrast, considering consider the ability illustrated in figure 2. One of interested in answering questions such as which media associates which media associates sales, which media generate the biggest boost in sales, or how large of an increase in sales is associated with a given increase in TV advertising. This situation was into her. Which media the okay. So at the beginning we looked at something called inference and prediction. And basically, I said we're not talking about prediction, it's just us treating the whole model as a black box. And in this case, we're talking about F. We don't really care about whatever happens within F. We just want it to give us the right, output, which is Y and the prediction. So these examples are actually like really interesting in the sense that uh, these examples are really interesting in the sense that um, uh, yeah, these examples are really interesting in the sense that uh, they give you a realistic uh, scenario where you know you so a realistic scenario where it's like if you're talking about inference like the example that I just read, the questions. So if it just goes from us just wanting to know which, the risk that we get based on the predictors, that's prediction. But if we ask questions like which media are associated with sales, which media generate the biggest boost in sales, or how large of an increase in sales is associated with a given response in TV advertising. When we get to ask such kind of questions, we don't want to treat F as a black box because every input variable is, we want to know how each input variable maps to the output, right? So I guess that's why it's called inference. Another example involves modeling the brand of a product that a customer may purchase based on variables such as price, store location, discount levels, competition, price, and so forth. In this situation, one might read so let me try to guess which let me try to guess which the problem is the notes are right here and I'm trying to guess. In this situation, what might really be between each variable and the probability of purchase. So another example involves modeling the brand of a product that a customer might purchase based on variables such as price, store location, discount levels, competition. One might be interested in the association between each variable and the So so um inference and prediction are, as I have said a number of times, that they are very important concepts. And so I think the best way to look at this, based on these um, definitions, right? Based on these questions, so examples, right? Is this uh, find a partner, right? You meet something that interesting, and for prediction, if we try to make this a prediction problem, we would say, is this partner it is so, this is actually a very good example. If you meet somebody, a partner, right, like someone, whatever you're into, and when you look at them and you're talking to this person, If it's a prediction, the only thing I would say, based on the people I've been with in the past, would my relationship with this person work out? Just gives us the output. Yes, you know, looking at this person, and maybe you could be going off of, the vibe in that moment. But when we try to make it an inference problem, that is where you always have a lot of questions. Questions like, this person is talking a lot. You know, is this something that I am willing to put up with? This person, like assurance, is this something that I can the more questions you ask, you not only try to relate them to the response, but you try to understand how they lead to the response, if that makes sense. you know so that's the difference between prediction and inference. Inference is basically you dotting your i's and t's to understand how you come up, to the conclusion. And prediction is just basically getting to the conclusion without necessarily uh, being too concerned with how you got to the conclusion. So that's what basically that is. Depending on whether our ultimate goal is prediction, inference, or a combination of the two, different methods of estimating f may be appropriate. For example, linear models allow for simple and interpretable inference, but may not yield as clear predictions as some other approaches. In contrast, some of the highly nonlinear approaches that we discussed in the later chapters of this book can potentially provide quite accurate predictions for why, but this comes at the expense of a less interpretable model for which inference is more challenging. Mhm. So, the statement is very interesting. I think it leads to this concept called the interpretability versus complexity or flexibility. Basically, the rule is that the more flexible a model is, the harder it is to interpret. And the more interpretable a model is, the that's what the less flexible it is. So these seem like two very innocent, easy concepts. If it's very interpretable, it means it's not very flexible. If it's very flexible, it means it's not very interpretable. But when you go deeper, like further, this is what leads to concepts like, you know, on the very flexible side, you have the deep neural networks, and then on the very interpreted side, you have, I don't know what, like isolation tree, SVMs, I would say that either too complicated or neither, I don't know. But yeah, so basically, this concept of, trying to find, uh, so do you see how this like book builds up from teaching you about predicting inference and then telling you about, you know, which you can pick. If you're going to inference, you're very, like interpretable. But it's if the model that you pick is very interpretable, it means it's very interpretable. It means that it might lead to I don't know if I remember this very correctly, but I think this might lead to the concept known as Okay. Okay. Where were we? What did I say? Oh, okay. If a model is very interpretable, it means it's not very. Yeah. So if a model is very interpretable, it means that it's less flexible. And the other word for flexibility is flexibility. So this is something. So this book, so like the goodness about it is kind of the badness about it in a way. It says things in an easy way, and sometimes it comes off as not important. But this statement right here, which says, in contrast, some of the linear approaches that we discuss later in the later chapters of this book uh, provide quite accurate predictions for why, but this comes at the expense of a less interpretable model for which inference is more challenging. This just seems like an innocent statement, right? This seems like uh, an innocent statement, but this is actually something that's very important. That's literally like a whole field on its own. So basically, when you have interpret, I just choked. So basically, when you have a very interpretable model, so it's like this. It's like this basically. When you have a very interpretable model, it means that it is less flexible. And when you have a very flexible model, it means that it's interpretable. Now, the big problem with that is that when these two concepts leads to, like, they lead to very serious concepts called bias that, that lead to underfitting or overfitting, which is basically when you have a very interpretable model. The problem with that is that I think I really choked on speed, So when you have a very interpretable model, uh, it means that it's very like it's less flexible. Now, what that translates to in the real world, like in a practical sense, is that this, you know, even though you might want a model, even if your goal is inference, you it doesn't necessarily mean that you want a model that's very interpretable. Because if a model is very interpretable, it means that it might lack the ability, patterns, and the relationships within the data. They're creating an oversimplistic output from the data, And this is called underfitting, where, your model just can't, the model can't capture the true relationships within the data because it's too simple and the relationships are too complex, therefore underfit. But when a model is very, what's the word? But when the model is very um, flexible. It's very complex. It leads to overfitting. This is, a phenomenon where it's like the model is too complex such that it captures all the other noise in the data, which are unique. So it's like this. When you're training a model, you have three data sets, right? The training data, the valid data set, and the test data set. The training data is the data which the model is trained on, right? And when you have a situation of overfitting, the model captures the uh, noise within the data, the random noise within the data, such that when it's time to, test the model on real world data, which is the test data set or the validation data set, it performs poorly because of the fact that the noise it captured during training exists in the training data set and nowhere else in the world. So whenever you test this model on different data, it just can't perform well because of the fact that it tracked or mapped the noise within the data. So yeah, that's what basically it is. Okay, let's not waste time on this. So how do we estimate F? Throughout this book, we explore many linear and non-linear approaches for estimating F. However, these methods generally share certain characteristics. We provide an overview of these characteristics in this section. We will always assume that we have observed a set of n different data points. For example, if we were going to observe n is equal to data points, these observations are for the training data. We will use these observations to train and teach our method how to estimate xi represents. Okay, this is the point where we start getting into, you know, numbers and stuff. We assume that we have observed a set of n different data points. For example, in figure 2.2, we observed n is equals to 30 data points. These data points are called the training data because we will use these observations to train and teach our method how to estimate f. Let sub I represent the value of the jth predictor or input for observation I, where I is equals to n and is equals. Correspondingly, let yi represent the response variable of highest observation. Then our training data consists of x1, y1, x2, y2, xn, x1, where xi, x sub I is equals to x sub I1, and so forth. Triangles. Our goal is to apply a statistical learning method to data in order to estimate the unknown method to the training data in order to estimate. Our goal is to estimate the amount. Our goal is to apply a statistical learning method to the training data in order to estimate the unknown function f. In other words, to find the function f hat such that y is equivalent to f hat x for any observation x. Broadly speaking, most of the is that can be characterized as the parametric and non. I think they need a 5 minute break. Let me just try to. When you study for a long time, you lose focus, and that's basically you know, what's happening to me right now. So my friend, so my friend just texted Zendaya. this is this is really fun. My friend Zendaya and said, "Uh, you're an inspiration, and I absolutely love everything about you. Keep being you." Like, bro, it's so funny. I mean, all done that, but it's so funny. Keep being you. What's that supposed to mean?
the forums.
There's nothing click to it, so then come data from bigger definition. Very hard to play word. Let's discuss it. So here's on original relationship with response with evidence for us. We can see that in the fifth location quite true. Okay, now that we have looked at a number of things, it's time to compress everything we've looked at into one thing, which is I don't know how long this has been here, but I just drank it. Okay, so now before we look at this subtopic that's underneath here, the trade-off between prediction accuracy and model interpretability. Let's try to summarize everything that we've looked at um into into what? Let's summarize everything that we've looked at so far so that we can see statistical learning is because that's the topic or subject that we're looking at. And were we learned that statistical learning refers to set uh, the vast set amount of tools that we can use for predicting F. But before we even get to F and whatever, we learned that statistical learning models, a statistical learning is a vast set of tools used for an data. Right. So basically, when we're talking about AI, machine learning, artificial intelligence, whatever you name it, at the core of everything is the data. This is why you hear think, it has 70 billion parameters or 70 whatever tokens. All that stuff is just data according to my level of understanding so far. I understand that is that. So, anyways, without any further delay, yeah. So we understood that statistical learning is just the first set, uh, you know, the first set of tools that we use to understand data. And another thing that we looked at is that when we're dealing with statistical learning, the ways in which the two types of problems that we might encounter. And these problems are supervised and unsupervised statistical learning methods. And the two methods basically statistical learning and supervised and unsupervised. When we're talking about supervised learning, we're referring to the kind of learning that is sorry, let me just try to do something. Uh, yeah, so when we're talking about statistical supervised learning, we're talking about like, it's working. Just trying to see if my live is okay. So yeah, when we're talking about supervised learning, we are referring to the kind of learning where we have labeled data. In the real world, I don't know if you guys know this, but data is so important. Like everything that we do is data. And for the people that are out there, the data brokers, the vendors that are out there, every little thing that you do is important to them. Like just open my phone and which app do I open the most? Like which app do I spend the most time in? And think of it this way. Imagine all bad habits that you have. Let's say you like to scratch your butt when you're alone in your room, or you like talking to yourself when you're walking or when you're alone, or you fantasize a lot. All those little habits that you know a lot of that you not necessarily like for people to know. They're not bad or anything, but it's just something that you know nobody's supposed to know about. What if those little habits, what if there was, what if there was something around you that every time you did those little things, it was being recorded and someone had access to it? Now, of course, you'd say, okay, I necessarily want someone to know about this, but even if they did, I mean, it's nothing. I don't really care. You don't really care. Well, that's where it's interesting. Even though you might not care, there's somebody who actually does care out there because they, with that information, can find ways to exploit your habits and your behavior in terms of the things that you do. That's the reason why, people say, when I'm talking to myself, my phone, I starts, suggesting the things that I was talking about. Well, some apps have good access to your microphone, they're listening in 24/7. And not only that, but the data is so valuable because to the businesses, the large the mega corporations out there, they rely on little pieces of data to actually gain an understanding of, an understanding of uh, the demographic, like the customer base, the people, what people are into. Let's say if you like to scratch your back, I don't know why I'm using that example, but hey, and you do it in private, you might not be the only person who's doing that. There's millions and millions of people who are doing that. And to a mega corporation, that right there is a business opportunity. That's an opportunity to make billions off of that. Maybe there's a new butt scratcher thing, machine that is there, and you never even knew about this thing, and just the thought of seeing it, this would actually be nice to have. This is how data works, and this is why it's so important. But then the biggest problem is that there is this concept known as big data. It doesn't really necessarily refer to data being big or a lot, although you'd be wrong to think of it that way. But big data just refers to important data, you know. But data, there is so much data there. Like there's so much data, like there's a lot of data, and this data being so much, it is not only hard to store it, but what's even more hard is to make sure that this data is of the highest quality. You remove the missing values, you make sure that there's as little noise as possible. You just label it. For instance, you have you are training what do you call these models, like image recognition models, right? And you want to classify it to say this is a dog, this is a cat, this is a dog, this is a cat. For someone to label that data, you know, there's types of data out there, and the process of labeling them is just so hard, which is why if you want to, you have two options: supervised and unsupervised. The labeled, which is just the example that I just gave, is so expensive. It is very expensive in most cases, especially if your goal is to create a scalable model. It is very expensive because one, not only uh, because the whole process of actually finding the data and working on it is very hard. It's very, very hard. But if you don't want to, you say, hey, you know what? I don't have like millions or thousands of dollars to spend on, labeled data. You have the alternative of finding a cheaper alternative, which is unlabeled data, which will, lead you to create an unsupervised model, which in most cases is where the data has to, you have to, you have to perform an exploratory analysis, which, depending on how big your data set is, it would be really hard to remove all the missing values to just make sure the data is just decent enough, for it to be usable. Because everything starts from the data. Without the data, you you understand what the problem is, and then you think of what the kind of data you need to. The kind of data that you get, you need to make sure that it's of quality, because If it is no, your model will be trash. I don't know if you guys are following this, but basically that's how it breaks. So we looked at supervisors and supervised machine learning, statistical learning approaches. Basically, we just say AI or whatever. So when you move forward now from this, we came across an actually before we even talk about the equations, there's a very important statement that we came across, which is that um, the input variables are sometimes called the predictors, the inputs, or just the variables, or they're sometimes the independent variables. And then another statement told us that the output variables are called the output variables uh, or the dependent variables. And it is from this relationship between the dependent and the dependent variables that we go to establish an equation from this relationship, which is the equation that y is equals to f of x plus the error 10. This equation moved from being this to something that later turned into, uh, what ordinary least squares method, the equation put in uh, regression models. So, yeah, so this equation basically told us that when we looked at it, oh, it's basically like high school equation of, y is equals to mx plus b. And we, from that equation, learned that f is the systematic information that x tells us about y. And y is our desired output of, for a give from a given input, so to say. And e is the error term, which is the irreducible term. And this irreducible error is basically, in simple words, the the what do you call it? The irreducible error. The irreducible error, in simpler terms, is the the inherent noise within the data from X that cannot be uh, uh, cannot be captured by X, no matter how sophisticated our model is, so to say. And it's the example of health, of weight that I gave earlier, saying if a person, we can't tell someone's weight off of just based of like of their height. Of course, we can say, the taller you get, the higher chances of you, being slimmer, because it's scientifically correct, I guess. But we just can't accurately measure someone's weight, predict someone's weight off of that, because there are a lot of factors that go into, someone's actual weight. You can say, okay, he's 7 foot tall. He's likely around, I would say, 160 to 170 pounds. But then you don't know the person's life story. You don't know the person's, eating habits. You don't know if this person works out. All those factors. These are, in reality, the irreducible error where it's like there's always going to be certain factors for every variable that we just which just lead to, always being an error in our prediction. So yeah, but so what were we looking at? We looked at this equation where blah blah blah, and f being the thing, and now what we need to talk about is, since we know, okay, we can either use a supervised or unsupervised approach where we want to train a model, but another question we need to ask ourselves is this: are we interested in the are we interested in the outcome, or we're just interested in, you know the the relationship between the variables of how everything works? If so, if we're only interested in, let's say, uh, So I've been doing this live, like no one's come around, and then someone suddenly comes, and I'm like, "Ooh, someone's watching me. I hope I don't mess up." That's so funny. But anyways, yeah, we looked us again. Yeah. So when we decide on supervised and supervised, now another question that we need to answer is: are we interested in only the outcome or the output of the model, or are we more interested in the relationship of you know how the outputs lead the inputs lead to the outputs? And your question, if your answer is the first, the former, then we call that prediction. If it's the latter, it's inference. Prediction is basically a concept in statistical learning where we uh, are more interested in creating a model that only gives us our desired output. If we give it a certain input, we want a certain. That's all we care about. But when we're talking about inference, we're basically concerned about how each we're more concerned about the relationships within the data. It leads to certain outcomes, so to say. And in most situations, I think that for most situations, like especially for companies, I would think that inference is like a more like scenario because prediction is kind of like one dimensional, so to say. It's like this, this is what I want. I mean, in basic terms, I would say it's one dimensional. This it's not, but it's like it's just focused. It's just not concerned about the model, so to say. Yeah. And inference is, as I explained, is more about the relationships. So in practice, how do these scenarios look like, the prediction and the inference? To start with prediction, we just want a model gives us, let's say a football match. We're watching a football match, and we want a model that can tell us which team is going to win. If it looks, the team's past performance, if it looks us, so we can create a model, and this model, if it's a prediction model, it's going to look at the team's past performances and say, this team is going to win this game, but this team is going to win or lose this game. But when we're looking at inference, there's a lot at play, which is it moves from just looking at the team's past performance, but rather it starts to ask questions. Uh, what are the weather conditions? Is the team playing at home or away? How did the team perform? How does the team perform when they're playing away? So inference creates these questions which turn into, I guess, predictors, or variables like input variables. And so we want to be able to map each variable to the outcome. Like how much of every var does like how much does each of these variables play a role in the output, so to say. And yeah, so this been prediction is. And apart from that, I think we looked at parametric and non-parametric uh approaches of like that we can use in statistical learning. Basically, uh so now, okay, uh if we choose so another thing that we looked I just talked about it, but it's the next thing. We haven't looked at it yet. I talked a lot about it in this entire stream, I guess. Another thing that uh, oh, let me take a picture. I like taking pictures because it's like, I one day want to look at, some of this stuff and be like, I used to stream to, like hours, with zero viewers and stuff. Yeah. So, what am I trying to say? Another, I feel like Did I have a flu or something? Um, so before we looked at parametric, we looked at oh, yeah. So parametric and non-parametric ways of approaches of training models. Approaches of training model. So basically, when you decide, supervised, unsupervised, prediction, inference. When you decide all these things, another thing that you need to consider is uh, another thing you need to consider is something called parametric methods and non-parametric methods. So what basically means is when you have, you understand your data, its inference, its prediction. There's an approach that you can choose to take. So of course, no, there's an approach that you need to take where it's like, am I going to use a parametric or a non-parametric approach? Basically, it depends with your goal. You know, at the end of the day, it's about the problem that you're trying to solve and the output you're trying to achieve. So basically, it's like when it comes to this question of should I use a parametric or non-parametric method, it comes down to this. A parametric method is basically a method where a parametric method is basically this method where it's like you're I just lost my train of thought. The parametric method is basically a method where you so mind you everything that we're talking about, like everything about this book and this statistical learning course comes down to one thing, and that is if everything that we're doing just comes down to estimating if according to what we read. That's not saying, of course. So we want to estimate f, right? When we're using a parametric approach, we say something like we assume a function of form or shape of f, and you know, yeah, we assume a function of form of x. So we assume a function of form or shape of f, and what this means is basically, we can assume a relationship of f in x that is, linear, so to say. We can use linear, so to say, like linear regression. So the easiest way to explain this is this: you have a problem, right? How can I? Let me try to see if I can come up with a better example. So you have a problem, and you want to know which is the best approach to take. It's like this. Hmm. Hmm. I think the best example would be something like, imagine you're looking at the clouds and you're trying to determine whether or not it's going to rain. Of course, you can tell that, nah, this doesn't make sense. Okay, let me just explain it this way basically. When we're talking about parametric methods, it's basically a method where you assume a form or shape of f in x. F is the systematic of that x tells us about y, and y is basically the output that we are trying to get. So when you use a parametric approach, you're basically assuming a certain relationship of f uh, in x, and this relationship can be something like f of x is equals to, I don't know if this is called beta here, but I'll say beta uh, x1 plus beta 2 x2 plus beta p x plus the error term. So a linear relationship of f in x. So now this means is that you imagine, so so yeah, You know what? This this is, I don't know. This is, I feel like this is a lot of study time, but like this is actually the first time where I'm studying like with very minimal breaks for this kind of time. I usually study like using the Pomodoro technique, and yeah, it's messed up. But yeah, what I'm trying to say is you assume a certain relationship of f and x, and you can say f is linear in x. And what this means is you your model is going to map the data or train using a linear regression, I guess, a linear approach. But this raises the question: since we do not know the actual relationship of f in x, how can we know for sure that it's linear? You have, of course, say f is linear in, x, but you have no proof to know for a fact that it's actually linear. So this actually leads to a problem where it's like, if f is definitely not linear, because a linear relationship, I would guess, is something that is very unlikely, I guess. I mean, it depends on the situation, I guess. And if it's not linear, it means that your model will be very bad. Like the training process will be very bad. And I would guess we'd be using the ordinary least squares method, since it would be a linear regression model, I guess. The learning process would be really, like, really bad. Your model a very awful accuracy because of the fact. Imagine you're teaching. It's it, it, you're you're teaching it using a relationship that's non-existent, basically. So it won't capture the actual relationships that are indeed within the data. So now this leads us to non-parametric. Non-parametric approaches, of course, are the opposite of the parametric ones, where you assume a relationship. In this case, you don't assume any relationship, but rather you just, you know uh, how would you actually do the non? Yeah, yeah, yeah. So one thing I forgot to mention about the parametric approach is that it has this advantage of having to having to estimate f s- down to a few which are the beta variables. But then when you're talking about parametric approach, you don't have that advantage anymore. You try to estimate f in x as close as possible to x, right? They're trying to do, which from that definition alone, you can easily tell that this is a tedious and long and cumbersome process. That's like, you need more data points to do that, which is a very, which is a very, which makes the entire thing hard. And another thing is the concepts of underfitting, overfitting have literally been in everything that we've looked at so far. For instance, because of the fact that parametric um, methods assume a certain relationship, they assume a certain ownership of f and x, we have a problem of, if it is not the actual relationship, if f and x is not linear, which is very likely, then we won't be able to capture the true beautiful patterns within the data. It's just underfitting, an overly simplistic model, which poorly captures the data. And then non-parametric methods are basically trying to not assume any form, any shape. They don't do that, but rather they try to estimate f. And so they closely follow the data, and by doing so, they capture the noise as well, which in this case they would lead to overfitting, which is just the relationships that are within the data such that they capture the noise that is useless to what we're trying to do. So that's what we looked at so far. Yeah. And now I want to have a break. Just a little few minutes. I'll be here though. I think I'm hungry.
My phone is gonna.
I think it's gotten to a point where I'm actually hungry. I want to have something to eat. And you just can't study one subject for more than 3 hours and not lose your focus, no matter how disciplined you are. It's right for me to end the stream right now and possibly do it again some other time, I guess in the morning, which will be nighttime for the people that most likely might watch it. Yeah, so yeah, I guess I want to have something to eat, y'all. Should I end the stream or nah? I want to fucking end the stream. Bye.